Hello friends, we are going to continue our discussion on tight binding model in this lecture. I already have discussed the technical details of tight binding model for a 1D lattice. In this lecture, I am going to show how to extend to higher dimensions. I am also going to discuss how to build the tight binding model starting from the isolated atoms. Now, let us extend our tight binding recipe to a square lattice. Step 1, select a row. Diagonal element in the ith row corresponds to the ith atom. Step 2, identify the nearest neighbors of the ith atom. In case of square lattice, there are 4 nearest neighbors, say A, B, C, and D. Enter -T in 8th, bth, cth, and dth column of the ith row. Let us take some example. Say the 5th atom. First, we have to index each lattice site. This is the 5th atom sitting at the 1, 1 position in the lattice. Left hand side neighbor of the 5th atom has an index 1. So we go to the 5th row and the first column. That means this side. And we put -1. Right hand side neighbor of the 5th atom has an index 9. So we have to go to column 9 in the 5th row. That means this one. And we enter -1. Top neighbor of the 5th atom has an index 6. Thus, we have to go to the 6th column in the 5th row. That is this column. And we have to enter -1. Bottom neighbor of the 5th atom has an index 4. Thus, in the 5th row, we have to go to the 4th column. That is this one and enter -1. Rest of the terms in 5th row are equal to 0. This is the Python code for the square lattice. I show only the portion to build the neighbor list and construct the Hamiltonian. Rest of it is very similar to the 1D code. First step is to index each site. We have a square grid with each grid point having coordinates like 0, 0, 0, 1, 0, 2, etc. Using a for loop, I index each grid point. For example, 0, 0 point has an index 0. 0, 1 point has an index equal to 1. And 1, 1 point has an index equal to 5, etc. Next, I build the neighbor list. Let us take mn site. In the code, I have used I and j in place of mn. The right hand side neighbor is m+1 n as defined here in the code. The left hand side neighbor is m-1 n as defined here in the code. The top neighbor is m+1 as defined here in the code, and the bottom neighbor is m(n-1) as defined here in the code. Note that I also have implemented periodic boundary condition in this code. For example, if we take the 14th atom, which is at the edge of the box, it does not have a right hand side neighbor if we do not have periodic boundary condition. If we have a periodic box, then atom number 2 is repeated periodically over here. As a result, the right hand side neighbor of atom 14 is atom 2 if we have a periodic box. This is what is implemented in this line of the code, and similarly for other neighbors. Then I construct the Hamiltonian matrix. I find the nearest neighbors for each atom. There are 4 nearest neighbors, and I enter minus t in the corresponding terms of the matrix. This is the code for the 2D square lattice. I index the atoms using the for loop here. Then I build the neighbor list here. I construct the Hamiltonian here. The Hamiltonian is diagonalized to get the energy eigenvalues, and then I calculate DOS here, and finally the density of states is plotted in this step. This is how the density of states looks like for 2D square lattice. This is the analytical result. We get a good match. Density of states for a square lattice have a logarithmic singularity at e equal to 0. Finally, let us discuss a 3D lattice, the simple cubic lattice. I just show how to get the neighbor list and leave it as an exercise for you to write the rest of the code. A lattice point has 6 nearest neighbors in case of a simple cubic lattice. 1, 2, 3, 4, 5, 6. I have shown the coordinate of each lattice point. It should not be too difficult for you to write the code using our tight binding recipe. Now we know technically what to do to get energy eigenvalues of an electron in a periodic potential using tight binding model. Let us now see how do we get tight binding model starting from wave functions of free atoms. This is also known as linear combination of atomic orbital approximation. Approximate wave function for an electron in the whole crystal is a linear combination of wave functions of isolated atoms. So, d psi is the wave function of an electron in the whole crystal. And this is a linear combination of atomic wave functions. C is a constant and psi is wave function at nth site of lattice. For example, this is the nth site. So psi is the wave function localized at this site. Since we are talking about a lattice, the wave function must satisfy Bloch theorem. So psi k of x must satisfy Bloch theorem. For that to happen, these constants C, K, N should be equal to 1 by square root of n, where n is the total number of lattice sites e power I k capital X n. So capital Xn is a lattice translation vector such that capital Xn is equals to n times a, where a is the lattice parameter. That is the distance between two neighboring sites. Thus, Ckn is equals to 1 by square root of n e power I k n times a. So, we can write the wave function as psi k of x is equals to 1 by square root of n sum over n e power I k n a, where small n is an integer, times psi. So small psi is the atomic wave function localized at the nth site. Let me prove that psi satisfies block theorem. So we write psi k x plus capital T, where T is equals to m times a, where m is an integer and a is the lattice parameter, such that T is a lattice translation vector. This is equal to 1 by square root of n sum over n e power I k n a, and in place of small x, now I replace small x plus t minus xn, and this is equal to 1 by square root of n sum over n I multiply with e power I k t and e power minus I k t times e power I k n a times psi x minus capital Xn minus t, and this is equal to e power I k capital T times 1 by square root of n sum over n e power I k times na minus ma. So I just use the fact that t is equals to ma to write this line times psi of x minus xn minus t, and then this is equal to e power I k t times 1 by square root of n sum over n e power I k. So small n times a is equal to capital Xn, and small m times a is equals to t. Times psi x minus capital Xn minus t. Now note that both Xn and t are lattice translation vector. That means xn minus t is also a lattice translation vector. This implies that this term is equal to psi k of x. Thus, we have psi k of x plus t is equals to e power I k t times psi k of x. In conclusion, the wave function indeed satisfies the Bloch theorem. So we have obtained the wave function of an electron in a periodic potential by using the linear combination of atomic orbitals. Small psi is the atomic wave function centered at atom n, and I just rewrite this equation by slightly changing the notation. For the atomic wave function, I just write a subscript n. Now let us calculate the following terms: n, h, n. This is equal to integral psi n star h psi n dx. Note that these are small psi's, that means atomic orbitals. So this is equal to E naught, which is some constant. This is the h n n, that is the diagonal term in Hamiltonian matrix. Next, we calculate n plus 1 h n, which is equal to integral psi n plus 1 star h psi n dx, and this is equal to minus t, and this is one of the off diagonal terms of the Hamiltonian matrix, h n plus 1 n. Next, we calculate n minus 1 h n, which is equal to psi n minus 1 star h psi n dx, and this is equal to minus t, and this is the another off diagonal term of the Hamiltonian matrix, h n minus 1 n. For any value other than n, n plus 1 and n minus 1, the integral is 0. So this is the wave function of an electron in a periodic potential obtained by linear combination of atomic wave functions. Okay, so now let us try to calculate the energy eigenvalue for this particular wave function. This is given by integral psi star h psi dx, which is equal to 1 by n sum over m n. So first I write psi star. This is equal to e power minus I k m a times small psi m star h, and then I write psi, which is equal to e power I k n a psi of n dx, and this is equal to 1 by n sum over m n. This term we can bring outside the integral, and then we have integral psi m star h psi n dx. Note that we already have evaluated these integrals, and this is also related to the mn element of the matrix. Now, when m is equals to n, this integral is h n n, and this is equal to 1 by n times epsilon naught. When m is equals to n plus 1, we have h n plus 1 n, which is equal to 1 by n, and since m is equals to n plus 1, this term is equal to e power minus ik, and we know that this integral is equal to minus t. Now, when m is equals to n minus 1 h n minus 1 n, so this term is now e power plus ik, and this integral is equal to minus t. Thus, we have e of k is equals to 1 by n sum over n e naught minus t e power ika plus e power minus ika, and this term is equals to 2 cos k, such that we get e naught minus 2t cos k. Thus, the energy dispersion relation is E of k is equals to E naught minus 2t cos k. Note that E naught is a constant term, and without any loss of generality, we can set it to 0. That is what we have done when we have written the code.